Assalamualaikum and a very good afternoon. I obit to Dr. Shah and all of my friends who are watching this video. Today, our group, which is group 10, will be presenting about the role of polymers in everyday materials. Our group members consist of myself, Mersa Ana Sofia, On Yushwen, Muhammad Afiq, and lastly, Muhammad Lutfi Adib. Now, I'll be presenting about the introduction for this topic. The definition of polymer are high molecular weight compounds synthesized through a series of chemical reactions. The importance of polymers is highly wear resistant and tough, exceptional corrosion resistance, versatile physical resistance, and lastly, lightweight and low cost. Its relevance to real-world context are versatility in daily life, technological advancements, and lastly, medical applications.
So for real-life application, we have syringe and medical tubing in medical field, which is made up from PVC. These materials are strong, lightweight, and resistant to chemicals. This characteristic makes them safe for medical use. Also, we have contact lens, which are made up from hydrogel polymer. This polymer is able to absorb water and remain soft. It also allows oxygen to pass through and make it comfortable for eyes. This shows that the polymer can design with specific property, which is flexibility, biocompatibility, and transparency to meet the medical needs. So in industry, we have rubber tires, which is made up from synthetic rubber. The polymer structure allows the tire to stretch and return to its original shape. And also for this, we have the insulation material, which is PVC that used in electrical wires. This will prevent electric shock and heat damage. This shows that the property of polymer depends on the structure of their chain and the amount of cross-link. This also determines the properties such as elasticity, strength, and heat resistance. Also in daily life, we have plastic bottle and plastic bags, which plastic bottle is strong and lightweight that's suitable for storing water, while plastic bags is flexible and durable. And also we have the clothing fibers such as polyester and nylon are also polymer, and these materials are strong, lightweight, and wrinkle resistant, which makes them suitable for clothes. And this shows that the polymer structure give them useful properties such as strength, flexibility, and also durability.
So I will be explaining the key concept of this. First, which is polymerization, the concept which the chemical process where small molecules called monomers are chemically combined to form a long chain-like network called a polymer, where this process typically occurs through two main mechanisms: addition of polymerization, where monomers add to each other without losing any atoms, and condensation polymerization, where monomers join with the elimination of a small molecule like water. The second one is thermoplasticity and thermosetting, the classification of polymers based on their thermal behavior and molecular structure. This explains thermoplastic, like polyethylene, have linear or brush structures that soften when heated and can be reshaped. In contrast, thermosetting plastic, like epoxy resin, undergo chemical change during curing to form a cross-linked 3D network that remains infusible and insoluble after heating. The third one is molecular weight and chain length. The physical properties of a polymer are heavily dependent on the length of its chain and the resulting total molecular mass. As the degree of polymerization increases, longer chain, the intermolecular forces between chains strengthen. This leads to a higher melting point, increased viscosity, and greater mechanical strength in the material.
Okay, so now I will continue to present the other three key chemistry concepts in polymer. So the fourth one is intermolecular forces, which is the van der Waals forces and hydrogen bonding. So now that we know how polymers are built, let's talk about what holds them together. So think of the polymer chains as a long piece of string. If we just lay them next to each other, they slide apart easily. But in chemistry, we have intermolecular forces, the molecular magnet that pull all these chains together. So now I will explain about the van der Waals forces. So these are the weakest force which acting like a static electricity. The longer the change, the more surface area there is for these forces to grip, making the material tougher. Next, I will explain about hydrogen bonding. This is a much stronger glue. If a polymer has a highly polar groups, the interaction between the chains will become very intense. So all this bonding will determine the material flexibility and boiling point. Okay, next for the fifth chemistry concepts, we have crystallinity and amorphous regions. Okay, first, crystalline regions. Imagine a box of neatly folded power cables. They are packed tight. They take up less spaces and they are very strong. This crystalline zone make a plastic dense, opaque and resistant to impact. Next, we have amorphous regions. Now imagine those same cables just thrown into a pile, tangled and messy. This is the amorphous state because there is more space between the chains. Light can pass through easily, which is why transparent plastic have high amorphous content. Okay, now we go to the last concepts of polymer, which is the biodegradability and chemical stability. For chemical stability, most synthetic polymers like PVC or polyethylene are built with carbon-carbon backbones. In nature, these bonds are like a lock vault. Bacteria simply don't have the keys to break them down. This leads to environmental persistence where plastic lasts for 100 of years. Next, for the biodegradability, to solve this, chemists are now designing polymers with weak links, specifically oxygen or nitrogen bond that can be unzipped. So that's all of the key chemistry concepts of polymer.
For our group discussion, the advantages and limitations. Polymers are essential due to their versatility and low cost. Their lightweight reduces fuel use in transport, but their environmental persistence is a major drawback. Most plastics are non-biodegradable, leading to significant waste in landfill and oceans. For future developments or trends, we predict a shift toward green chemistry and bio-based polymers derived from renewable sources like corn or cellulose. Chemical recycling, breaking polymers back into monomers, will likely become the standard for a circular economy. The impacts on health, society, and the environment. For society, polymers provide affordable medical gear and tech. For health, concerns exist regarding microplastic in our food chain and chemical leaching. Environment, while they reduce carbon footprints by saving weight, fossil fuel extraction for production remains a burden. All in all, while the chemical versatility of polymers have revolutionized modern life through affordable and durable materials, the focus must now shift toward sustainable green chemistry and circular recycling to resolve the environmental crisis caused by their molecular stability.
Now I'll be presenting about the summary for this topic. Polymers are large macromolecules that are created through chemical reactions using light elements such as carbon, hydrogen, oxygen, and nitrogen. The crucial connection between the field of chemistry and human advancements is demonstrated by how the physical structure characteristics of a polymer, varying from gaseous forms to solid structures that are influenced by shifts in its molecular weight. As the unseen foundation of contemporary life, these substances are present in countless items, including the synthetic fabric in our apparel, the natural proteins and plastic wrappers in our food, and the rubber tires and resins utilized in transportation. In the end, the adaptability of polymer chemistry has significantly transformed everyday life by offering innovative, lightweight, and high-performance design options that were not feasible with conventional materials. That is all from us. Thank you.